Okay. Hey everyone. Hey Anders. Congrats. You are climbing up that first leaderboard, Anders. Let's see. Actually, you probably. Oh, you might have just passed Eldritch. No, wait, no, that's Joseph that I'm looking at. You're at number 5. Still, you're getting up there. Let's hop into the voice channel. Hey Rapture. So yeah, we're just starting on chapter 7 today. Um, Mangoes, hey, how's it going? And 7, like, you hated learning this? I hated the class that I took on E&M. I've been loving reading this book, though. Um, because the class I took, like, multivariable calculus wasn't a prerequisite, and so they had to avoid basically all of the cool stuff to me. But this book just, like, it's basically all multivariable calculus, and it's really cool. Spielurkin. Oh, neat. Yeah. Please go do that, Anders. Hey, Fenbucks. Rapture, yeah, I agree. And before I started doing this, I didn't think that I would agree. I used to not like physics. It's like algebra based instead. Oh, yeah. I don't like that because that's just like memorization. Hey, Fenbucks. Came here from Discord. Oh, welcome in. Um, yeah, I forgot that's a thing now, isn't it? Yeah, I do like math streams, like math like homework help streams, and then on Saturdays I do this reading group for electricity and magnetism. So usually this lasts for 2 hours, and then we switch into like normal like math help.
Here I am.
Oh, hey Fenbucks, how's it going?
Oh, good. You know, the usual angst of the Purcell Saturday.
Yeah, I did really choose out some 1-star problems so we could start and or end with one if that'll help.
Yeah, hopefully.
um, and Mangoes, I assume Anders is talking about there's an abstract algebra like reading group Discord server. If I can find the link quickly, I will drop it. Um, oh, where did I get the link from? But they have like people who can like be like guest speakers, I think, and they like present on things. Dang it, I can't find it quickly, but another math streamer. Oh, it's tomorrow. Okay, another math streamer, Penn Center, has been reaching out to different like math discords out there. So if you ask him or maybe Stooky, they would know what's up. Yeah, Andrews, if you don't mind. All right. Sorry about that, Fembox. Oh, and Chaotic Dude, hey. We're just starting on chapter 7 on electromagnetic induction. So the Saturdays are like the official E&M reading group. And we're going to choose some problems from chapter 7 to like work on. All right. Sorry about that, Fembox.
I think that algebra group, I think they're reading one of Arden's textbooks.
I think so too, yeah.
So, yeah, I figured that was out of my pay grade. I think they didn't start that long ago. I think they only started a couple weeks ago, but I figured it was, that and Purcell at the same time. No, no.
Oh, yeah.
Something would have to give.
um, this one won't be for much longer, though. Um, yeah, I still
Yeah,
want to follow along Penn Center's group, but I haven't. Sorry,
yeah,
what?
Oh, the one you mean the one he does on Wednesdays?
Yeah.
Yeah, I've been going. It's good.
Okay.
It's good. He's trying to read that book, another Morin textbook, and it's the hard one.
Yeah.
And uh, so on Wednesday, he was getting frustrated. I thought he was going to throw the towel in, but I think what he said he wants to do is just change the text, which I think is a good idea.
Yeah, that'd be a pretty rough introduction to physics.
Yeah. Oh, yeah, it was. I think he was it was honestly a real good show to stick with it as long as he did.
Yeah. So respect there.
I guess if you have a math background, you can sort of, try and challenge physics that way, just rush right into it. But uh, yeah.
Yeah, if you're good at the calculus, that does a lot of the heavy lifting for you. But I don't
So
know.
did you finish chapter 7? I didn't finish chapter 7. I only got about halfway through it.
I did finish it.
I think
I
I
don't know
got
that
up
I
to
understood it
mutual
all.
inductance.
Okay.
Yeah. I mean, I've read about mutual inductance and self-inductance before, but I'm sure I haven't read the details that Purcell would shine onto it.
Okay. Yeah, I think those sections were relatively short. I don't feel that. Yeah, like especially the second half, I don't feel very solid on. I guess do you happen to know like what does an inductor do in a circuit? It seems like it resists change in current.
Yeah.
Is that
Yeah, it's
your understanding?
yeah, it's I think it used to be called a choke,
Okay.
is what I think. So it's kind of like if the current tries to quickly change, the inductor will act in a way to reverse that change, right? I think that's what Lenz's law tells us. And didn't that come up early in this chapter?
Yeah, actually, I
Sort
happen
of
to be on that
saying
page
that,
now.
oh
Yeah.
yeah, there it is right on my screen. Sorry, I didn't even notice.
No,
Yeah.
I
So
didn't realize either.
yeah, so the induced electromotive force, the direction is such that the induced current creates a magnetic field that opposes that change in flux. So basically, if you want to think of it, it's kind of like if you have an inductor in a circuit, uh, if the current tries to change, uh, it acts in a way to sort of stop that change just for a second. How does it work? So it's capacitors and inductors are kind of like flip sides of the same coin. So an inductor wants to make sure that the current doesn't change, and the capacitor wants to make sure that the voltage doesn't change. Um,
Oh, so I was just wondering. It seemed like they have a similar end result in the circuit.
yeah,
In terms of like they have the same kind of decay if you just have like uh an RC circuit versus an RL circuit.
yeah, that's right. Did they go into that RL circuit stuff at the end of this chapter? Because I didn't get that far. It looks like they
They
probably do, right?
did
Because they're talking about energy stored in the magnetic
7.9.
field.
Yeah.
Yeah, okay. All right, good. Well, maybe I know a little bit about that stuff. Oh, yeah, I see
Yeah,
those.
that part wasn't
Yeah.
too bad. It's just the normal kind of diffy Q stuff.
Yeah. Yeah. See, that's the stuff that I'm going to be reasonably solid with.
Okay. Um so did one thing I'm still kind of like did you understand what they were saying with the flux tubes?
A little
There's
bit.
at one
Yeah. I
point.
mean,
Yeah, I felt like I
yeah, they
wasn't
were,
really following that.
I guess they were just saying yeah, there's the picture of it. They were saying like, so the surface of the tube is riding along the magnetic field lines, right? So
Right.
if you look at that tube that he's drawn there, like the surface of it has lines that are sort of on the surface, right? Continually on the surface. And so then the inside is so let's see. So fields that come in the bottom inside the tube have to come out the top inside the tube, right? And if you took any cross section of the tube, you'd have exactly the same magnetic flux through that cross section.
Okay.
I think that was the idea anyway.
Hmm.
I don't think I'd heard of flux tubes before, but that was the understanding I took away from it.
Okay. It sounded like some kind of like weird like other way of imagining how the divergence is zero, or like I think they were making a point like how like the
Hmm.
electric field you couldn't do that, so you'll eventually run into like a discontinuity, something like that. It's like a
Yeah,
nanotubule,
maybe.
but I don't know.
Yeah.
I'm not mistaken, the magnetic
I
field
bet.
lives on the surface here. Chaotic dude. Yeah, for these tubes, I think that's what they were saying, or I don't know. I guess do you want to get into some problems?
Uh, yes.
Yeah. Yes and no.
I mean, why not?
Yeah.
Let's give it a shot. Let's give it a shot.
Okay. Let's maybe let's build some confidence with a 1 star.
Okay.
So 7-Eleven. Also, 7-Eleven is funny. Essentially using their hand rule the best way to find direction. I think they're doing something a little bit different with the flux tube metaphor, but I don't know. You might be right, chaotic dude. Oh shoot, you know what? I pulled this one. It's kind of looking at some 1 star that wasn't completely trivial, but I need to look back at the self-inductance piece. See how this works. And actually, you didn't see. Oh man, maybe it was a bad choice of 1 star problem because you didn't read this part.
No, no, let's try it. Let's try
Okay.
it. It's 1 star. We gotta get it.
So
I gotta find my PDF of the textbook here. Here it is.
the inductance is the flux through the solenoid divided by the current.
Self-inductance, L. So, okay, wait a second.
Self-inductance.
Is that the one that's measured in henries? Is that what they
Yeah.
said? Yeah, okay. Yeah, self-inductance.
So we need the magnetic
So
field of a
when you do
solenoid.
circuit problems, yeah, when you have circuit problems and you have a inductor, the inductance they talk about is measured in henries. And they always use that letter L for inductors, the same way they use C for capacitors
Okay.
and R for resistors, right? So RLC.
Right.
So maybe I'll have some idea about this, maybe.
I went to chapter 6 and I found the formula for the magnetic field of a infinitely long solenoid, which I think is good enough since they say a long solenoid.
Okay.
It doesn't depend on L though. Maybe that's an issue. Maybe do they provide a different formula? Should it depend on L? Oh, it's because the small n in this formula is maybe the turns per length.
Oh, is that what it is?
Uh,
Because
yeah.
this is
Or
capital N in the problem.
the number of turns in the winding per meter length is a constant small n. Okay.
Okay.
So,
So,
oh god. Classic Excalibur. Small n is equal to big N over L. And so the flux through the solenoid, we can just draw any circle we want. Mu naught Ni over L times pi r squared. And I think L is just that thing divided by I. I don't know what this order of letters is, but maybe? We could check the units on this.
yeah, mu naught. What's the units on mu naught?
Tesla meter per ampere. Times n is number of turns. Okay. Times meter squared. Over meter. Oh, we need to. What are we expecting? What is a Henry?
Yeah, I know. That's another good question. What's a Henry?
Looking for it.
I guess it would be volts times seconds per amp.
Volt second per amp. You got it.
Okay.
Um,
So, and what's a Tesla? It's like
wait. Or an ohm times second. That's not helpful. Okay, yeah. So we want volt second amp. Volt second amp. So is it? The meters cancel, the turns we can ignore. Is a Tesla a volt times second? That would do it for us, right?
F equals QVB. I've been doing some problems with F equals QVB, and that's how I remember what a Tesla is. So B is F over QV. So it's a Newton over a Coulomb times meter per second.
Archidoma, thank you.
And coulombs per second is amp.
Thank you for the follow.
Newtons over amps times meters. So a Tesla is a Newton over an amp times a meter. Tesla equals Newton over amp times meter. I think that's right. Does that help? The amps would cancel. We didn't want the amps to cancel.
Yeah.
Oh no, the amps don't cancel. Sorry, my bad. It seems like we got too many amps.
Yeah, this seems weird. Okay,
What about
wait,
turns?
Newton,
Is turns like dimensionless?
I assume we could kind of write it off. Newton Coulomb. Okay, yeah. The book does agree with your definition of Tesla.
Oh, well, can we get rid of volts somehow? What's a volt in terms of amp? Ohm's law, V equals IR. So a volt could be a amp times an ohm, but now we got ohms. Oh, didn't you say we could
Coulomb per meter over Coulomb per second. Does something good happen here? S squared over that. I don't know about that.
a square second per meter? That's a Henry?
Apparently, doesn't feel good.
Wait.
No, it's
wait.
Coulomb times meter. Right?
I thought it was coulombs and joules. Joule per coulomb.
Joule.
A volt is a
Newton per Coulomb? Oh my god.
Oh boy. Units in physics. Good grief.
Ugh.
If only, every physicist didn't have to have a unit named after them, it would make things a little easier.
Exactly, and there's different systems of units named after different physicists.
Yeah.
Joule per Coulomb. Ugh. Okay, so Joule second squared, Coulomb squared.
Okay.
What's the difference between a Newton and a joule then?
A Newton is a
Because
joule. A joule is a Newton times a meter.
that seems like it could work.
Okay.
Or wait, joules a Newton times a meter. I this isn't no. I think this seems off. This doesn't feel good to me.
I think you're getting there maybe. But change that other Coulomb back to an amp again, because then we could get square amps down there. I think that's what we want.
Okay.
Yeah, because if we
Um.
is that gonna work? Cubic meters. I think that works. I think if we take this thing we had for Teslas and put it in here,
Oh.
I think we
Yeah.
get it
Okay.
maybe.
Because okay, from oh, the meters are. Oh, do we have a meter in the wrong spot?
I think it works.
N M A squared. What am I? I'm adding. No, yeah, okay. That turns I'm just gonna delete. So we get NMA squared. Oh, okay. I feel like that
Okay, so
probably could have been easier, but the units seem to check out then.
isn't that amazing? It takes 5 minutes just to verify the units. It's like, all right,
Okay.
so what does that mean? Oh, that means we're done, right?
Uh,
The self-inductance.
I
Yeah,
think we
so are you
found a.
thinking so this looks like what we wanted then. Mu naught pi n r squared over L.
I think so.
Good.
All right. I'm gonna cross our fingers.
It's got to be right.
Uh, mu naught pi r squared n squared. Oh no. Wait.
N squared. Oh, we're missing an n somehow? Hmm.
Yeah. Wait. You have to multiply the area by n? Oh, you have to do the flux through every single turn? So we're not doing the flux just through one circle. We're doing it through every single turn. Huh. That feels weird. No, I guess they
Yeah, I
have
don't really
the
understand.
same thing in the toroidal inductor thing. Um, magnetic field, the flux through, and I remember them like in one of these things they did in the rectangular toroidal coil. Oh, you might not have seen this one. They started by getting the flux just through one of the turns,
Okay.
but then they multiplied it through to get the flux through every single turn. I'm not sure why, but that is something you seem to need to do. Yeah, chaotic dude's confirming.
The flux is a magnetic field times the area, which is what you have, but that's only for one loop. Oh.
It might be like the definition of phi that I need to look at again. Um, because I was imagining it as just the magnetic flux through like whatever surface you might want to draw. I guess, well, it is. but we're supposed to apparently draw it through every single turn.
Hmm.
Hmm.
Radius r. So pi r squared is like the cross-sectional area. And for flux, you did the cross-sectional area times mu naught ni over L. That formula you grabbed from chapter 6, it says infinitely long solenoid BZ.
I thought it was okay if they said a long solenoid. I can look back at the answer and see if that's the one that they came from. They use the same formula. Hmm.
All that dimensional analysis, and it let us down because it was the non-dimensional term that we
Yep.
messed up.
Uh, that's not like the biggest mistake though. Like now we know.
Well, I don't get it. So it's got radius r, length L, and n turns. So capital N turns. Yeah. I just had to go back and read the derivation of that formula we used for the solenoid magnetic field. Yeah, I'm getting confused with the lowercase n versus uppercase n, I think.
Yeah, that part's a little bit weird. We were supposed to get an extra factor of n for the total flux through like adding up every turn. That part it feels weird to me, but I don't know.
It makes perfect sense, I guess, if we just did one turn, that makes perfect sense that if we're missing capital N. I thought when we did uppercase N divided by L, we were taking that into account.
Yeah, it makes sense what Chaotic Dude is saying. We're like we did kind of just find it for a single loop or like per loop, and the inductance should be different the more loops you add, but I don't know. I've got to reread that part where they were talking about like what type of fee you actually need for this inductance. I don't know.
All right.
Really
Well, it was
close on
close.
that one. Yeah.
Yeah.
I'll bring in number 3 looked interesting.
Induction. Inductance is proportional to square of number of turns. I'm sure I've seen that before too. I just hadn't remembered it.
Oh, okay. Okay. Number 3. Square wireframe with side length L has total resistance R. It is being pulled with speed V out of a region where there's a uniform B field pointing out of the page. Consider the moment on the left corner as a distance X inside the shaded area. What force do you need to apply to the square so that it moves with constant speed V? Well, I guess we just need to work out what force this frame is experiencing.
Hmm.
Um, and so we could, I hope I, like, we could just do that V cross that B and then figure out, I guess we need to do some kind of geometry with what that triangle is there, but they,
Yeah, we got a 45 degree angle.
right. What, I guess, can we like, what magnetic force is this thing experiencing? V cross B. Wait, I think it's experiencing a downward force?
B is out of the page. Yeah, okay.
Yeah, 2 degrees, it should be downwards. Okay. And so, how can we work on, we need to, okay, we probably need, maybe it's, we need to work out the change in flux through this thing, and that gives us the EMF.
Yeah, Faraday's law.
Yeah. XD, I don't know how to say your name, but yeah, we're kind of trying to work out how to find that magnetic force. Sen? Oh, okay, sounds good. Um, so we're pulling, V is going to the right, so the flux is decreasing.
Yeah, for sure.
This feels like a calculus related rates type of problem. Like, how fast is the area of this triangle decreasing
Yeah,
as
is the
that side
flux
moves
just
inward?
is the so the flux is just a it's just a function of the area, right?
Yeah. So the total area, while the square is still complete in the field, is L squared.
Yeah.
It is kind of tilted though, which makes it less easy. Um,
Well, the area we got right now is just x squared, isn't it? Because
yeah, we should write the area, I guess, in terms of x.
yeah, because if I think of this square here, I mean that's the same area that we're seeing that we have flux
Oh,
through right now. Because the two triangles we could just sort of
yeah.
yeah. So what do we do with that though?
Um,
Where was magnetic flux first defined in this textbook? Was it this chapter or the previous one?
I'm pretty sure it was this chapter, like the capital Phi.
Yeah.
I'm pretty sure it was this one when they talk about the loop moving through the field. Magnetic forces. ILB, where L is length of V.
So is it as simple as just B
Oh,
times X squared? Is that the flux, BX squared?
um,
But we'd have to take the derivative, wouldn't we? So we need ddt. So
it might end up being that. So,
tell me if this is right. I'm just going to write something down. So
yep.
if the flux was equal to bx squared, I don't know if this is true, then the rate of change of the flux would be 2bx times dx dt. And dx dt is our velocity, isn't it?
Um, that seems reasonable. I was trying to find the formula for that they did for like the loop moving through a magnetic field uh that wasn't tilted.
Yeah, like were they doing a rectangle? I forget.
Yeah. So they got QV B1 minus B2 W, and W is the length of one of the sides. Um, oh. Honestly, the more I look at your thing, the more I think I like it.
How do we relate? If it's true, how do we relate it to a force? What force do you need to apply to the square so it moves with constant speed?
Um, Now that you have the EMF, you can calculate I because it has resistance R.
Oh, we haven't brought the resistance in, have we? Oh, so the total resistance is R. So we probably have to find what fraction of R we're. Oh, no, because the current goes through the whole loop, doesn't it?
Um, I think we could
So
just
can we just do,
do
yeah,
Ohm's law on that. I don't see the
okay.
issue. XV over I.
Okay, so that would give us the current in
Oh, I
terms of
should have
things we
solved it for
know.
current, yeah. Um, I is V over R, minus 2BXV over R. Okay. And so
Now, how do we relate current back to force?
well, I assume we need to, like, that's going to inform the Q and the QV cross B.
Hmm.
Or Sen is saying there's a formula like ILB. I don't know if we have that.
Yeah, that's the bill I kept talking about. F
Oh,
equals
Bill.
bill. But it doesn't bill only work if you're moving it at right angles to the velocities at right angles to the wire, or is that not the case?
I don't know.
Yeah, that was what we were doing last chapter. Working out how much force we needed to.
Was that like on a ring?
We had that problem. Do you remember the problem where it was like a little U frame hanging down from a wire, and we had currents through the two parallel wires, and we
Oh,
had to find the angle it was hanging at?
yeah.
I think that's where we used that formula. Here,
Hmm.
I do know where it is in the book. Let me just find it.
Yeah, I'm just like I don't remember how we worked out that part of the problem.
Savar.
Oh, was it from that part?
I think it came up before that. Yeah, it's in section 6.1, page 283.
Mmm. Just the force from one wire to the other. I really? And we're considering like I I, I haven't worked out which direction the current is going to go here, but like we were considering like opposite sides of the squares, two different wires, and the current's going in opposite directions. Um, it's only through the left half of the square. Is a current only induced in the left part of the square? How does that make sense?
I mean, I guess it's induced there, but it would have to go around the whole loop, wouldn't it?
Yeah. The current is through the whole loop. Okay. The EMF is only induced there. Okay, and that potential difference is what makes the current. Well, I don't see how that ILB thing applies. These are at right angles. Well, I don't know like what how we're using that formula.
Um, yeah, how does that help us?
Okay, I mean, yeah, I might be more um satisfied with like the VO thing that Chaotic is saying. IDL cross B. Or it'll make more sense to me at least. Um Hey Ren. Yeah. Uh, okay, it's kind of I I want to just work out which way the current is going. It's like bothering me now. Magnetic flux is decreasing, is upward and decreasing. So this loop is trying to add upward flux to compensate for the losses. So the right hand
Okay.
rule says the current is going that way around, counterclockwise.
Seems good.
Um, and so I was wondering about that, I guess, for like the sake of DL. So I would say like DL would go that direction.
All right. Are we about to throw some Biosavar at this?
I guess so. If I can find it again.
I was reading another book today. It says Biosavar rhymes with Leo Bizarre.
I
So I think we got it right.
like that. Um, okay. And so this would give us the total magnetic field on that portion of the loop if we calculate it correctly, I think. What is R?
Now wait a second. This tells us how to. If we integrate that, we find a magnetic field strength, right?
Yeah,
Based
'cause
on angle.
that's weird. We're calling it B. You use this if you're trying to find the B field produced by a current. Yeah, the B. Right, so the uniform B field is already there. This thing, I guess this formula would find the B field that's a result of the induction, I guess, which we probably don't need.
Yeah, maybe not.
So
Okay, constant speed.
is it like I assume the I is helping us calculate the like if F equals Q V cross B, I assume the I is helping us calculate Q, like I dt V cross B or something like that. That's where I thought this problem was gonna go. That's going up with IBL? We did that, Ren. Essentially have Q DI dt. We change to dq dt di. Well, that's how I did for this. I might be wrong. We can now assume we added battery potential V to the left side and use other laws like Kirchhoff or something. Uh, I think Kirchhoff's doesn't apply here when you have changing magnetic fields, unfortunately. I don't, I just don't get how the IBL thing works here.
No, I don't either.
Which is why I want to do this way, even if it ends up in the same exact result. And then V cross B, since they're perpendicular, is just B times B.
Are we trying to get an answer here as a force as a number, or I mean, well,
It'll be a
are
function.
we trying to get a force that's like a, or are we trying to get it as a function of x? It
Uh,
feels like as x gets smaller,
the
our
force should be
force should get
decreasing.
smaller, right?
Yeah.
Yeah.
And so if we can just calculate the magnetic force, we just slap a negative sign on it and say that's the force that we need to apply.
U times dl dt.
I don't see where that's coming from at all, Sin. Also, welcome in Amit. Even if it doesn't apply here, I appreciate you like participating and sharing your thoughts. I guess, and yeah, links are turned on. So, I mean, I think I haven't seen this same form on your link right in the book as I put your link in. I think this is df equals idl cross b is probably what we want. Um, so if we plug in I minus 2b xv over r, L and B are perpendicular, so we can just say BL, and then I'm being messy with the vectors, but I'm not going to care about that right now. L, so the weird thing with L is that we have a turn in here, don't we? Then use trig to
I guess
turn.
we can
Oh, what?
do it in two parts, maybe.
Yeah. Or I guess L and X are dependent on each other, like Chaotic Dude is saying that we need to deal with that. Or well, L is a constant, but whatever. Ugh. Yeah, so um DL should be dx over sine pi over 4? Okay, because if that's length dx and that's length dl on my hypotenuse, from the geometry of the problem, we know that's a pi over 4 angle that I'm not doing a job of writing, so I always draw things too small. And then x is going... I mean, I guess we're going... Where are we starting? I guess we're going from the total diagonal distance, like from being completely inside the field to being... No. We're considering the moment when the left corner is a distance x inside the shaded area. You're asking add that moment x, what force do we need? Or at that moment where it's distance x, what force do we need?
Couldn't we just say L is 2 root 2x? Does that work? I mean, the total length L would be root 2x.
That's what I
Let's see.
was
We're
thinking
trying to
out too,
get
that it's x to 0, but the force is changing over time, right? And we're interested in the exact force when it's at distance x. Or No, I'm sorry. X to 0 is only this partial distance, like at this moment, until it's fully out. Actually, that might be okay. If we're only asking, like, from this moment onward, how much force do we need to keep it at constant speed?
So what's constant? B is constant, R is constant, V is constant, right? So X and L are the only things that are changing.
Yeah, and we
Say
said
L is,
dl is dx over...
DL would be root 2 dx, wouldn't it? I think that's what, yeah, that's what chaotic dude is saying.
Yeah.
Sine pi over 4, so that would be root 2.
Okay. So then, yeah, B, V, R, the root 2. And then we have x squared from 0 to x. And taking away the negative sign and flipping the bounds.
B squared?
Yeah, thank you. Oh, yeah, I put an extra squared.
That's all right, I'm watching.
I need it. R. So that's 3 and an x cubed, and then the other term is just 0.
How did you get an X cubed?
Why did I integrated it twice? Because it's just what I do. Just really love integrating things.
That's fun.
Okay.
So wait a second. Have we actually got an answer? Is this our answer?
I think we need. So this is the force from the magnetic field. I think we need to put a negative sign on it. Like the force we're applying to compensate is the negative to keep it at a constant speed v.
Negative.
Or like, you know, in the opposite, say magnitude, the opposite direction. Because I think if we're not compensating for the force, this ring is going to start to rotate, is what I'm imagining. Like the left side is going to come downward. And so we're putting an opposite force going upward. You think you lied me, so the force is downwards? But V cross B. Oh, that's the wrong V again. Oh my god.
When you said downwards, I thought you meant
Oh.
down the page, right? It's going down the page, isn't it?
Like that arrow that I drew here, but I used the wrong V. This wire has a V that direction, and that wire has V that direction. So you get a force going that way and that way. It's actually being pulled back into the field. Because we just use V's willy-nilly, apparently. And you can't always trust the V. They give you the problem for the V cross B. So there's actually, yeah, one force down there from the magnetic field and one force up there from the magnetic field. and the vertical components cancel, so we just get a horizontal left component. And that makes more physical sense, I think, because I'm imagining you have this thing on a hook or something and we're pulling it to the right, and that's our force that we're applying.
Okay, that makes sense. What I was trying to do in my head before was thinking of it as like two wires that weren't connected at the corner, and imagining the velocity as in two components, right? One's in the direction of the wire and one's at right angles to the wire. And in the direction of the wire, there shouldn't be any magnetic force, right? So I agree with those two arrows. They look right.
Okay.
Sort of like thinking of the components of the velocity, right? One going down and to the right, which the magnetic force will oppose, and the other one going up and to the right, which the magnetic field doesn't care about. Because anyway, I'm probably not making sense, but I get it. I get that. I get
Okay.
the directions of your arrows.
Yeah. All right. So I guess we can say it as like magnitude that to the right is our force that we're applying to keep it at constant velocity.
Isn't the negative sign telling us it's going right?
Um, yeah, X is, well, have we defined, I don't know what direction we defined as positive in this problem.
Okay. Well, anyway, we're basically saying it's going right.
Wait, you have to multiply a force by 2 sine pi over 4? Oh my god.
Hmm.
Did we only get it for one of the wires and that's why? Traveling Jack, thank you for the follow. Aero Engineer, I flipped the bounce because we had a negative sign in front. Traveling Jack, I'll be doing math help in an hour or so. It's on Saturdays I do this reading group for the first two hours and then I do math help. If you need math help in general, there are a whole, I don't know that any of them are live right this instant, but I just like to let new people in general know that there's other math help people out there too. But if you're willing to hold on for just like an hour or so, I'll be able to help you out. Or at least I'll take a look at it. Oh, it sounds like it might be a little. I had to be more about like the homework question, so I might not be able to help with yours. But if you want to post it, I'll tell you if I even have the background to talk about it. I guess. Um. So character is saying we only found the force on one of the wires, and then that force is pointing up and to the left. So we both need to multiply it by 2 to compensate for the force on the bottom wire and divide out sine pi over 4 to get the horizontal component.
Is that because it's ILB sine theta? But did we do a cross product? Oh, Don, didn't you say something about you were gonna not worry about the cross product? It was DL crossed with B, right?
Yeah, I mean it's always
What about that?
perpendicular, but sorry.
Yeah, you're right, it is. Yeah, DL crossed with B should be perpendicular.
Oh, I've seen at least the geometric series argument for that traveling jack. I might be able to have a somewhat intelligent thought on that. Yeah, I have a hard time figuring out, like, I can definitely see that we've accidentally only found the force for one of the wires. I have a hard time finding that in the math, though.
Is it to do with the bounds on the integral?
DL and B are perpendicular.
When we went
Yeah.
from DL to DX, we should have doubled it, shouldn't we? Because there's a
Oh.
L.
Hmm. Yeah, it could be that. But wait, well, I mean, Captain's saying we need another vector assigned pi over 4. Which gets, I guess we're finding the magnitude of the vector pointing up into the left. Okay. Um, yeah, I think it came from that geometry part that you're saying, where we made a statement about how the relation between DL and DX, that makes it only the upper part.
I thought that was where this root 2 here came from.
Um, I think by drawing the right triangle, how we did, we're only. I think as soon as we introduce trig, we're reducing it down to like the upper right triangle or the lower right triangle. That's why I think this thing is resulting in just the force on, one of the wires.
Yeah, okay. I agree with that.
Um, just one piece. I'm going to write in parentheses here. Um, so the force that we're applying then. Rizezi, thank you for the follow. 2 over root 2 over 2 times the negative of the thing we found is the force that we're applying then. So we get negative 4b squared. Oops. I think I'm okay with this now. I don't know how you feel about it.
I feel okay.
Okay. And
Is that water you're swigging there, or is that vodka? I feel like I need some.
Oh, that's the mystery now, isn't it? I need a little bit of courage for these reading groups. And Edison, I just don't find it that hard to write with the mouse personally, but I did just recently buy like a tablet to write with too. There, you can get them pretty cheap.
Yeah, the tablet looks nice. The handwriting looks nice.
Oh, good. This is number
I
3.
got one kind of like yours, but I think I got a much smaller version here.
Oh, okay. Mine's like, I think it's like 4 inches by 3 inches or something. It looks a little bit bigger. I thought I remember seeing on the Amazon page that it was 4 by 3. Oh wait, we didn't do part B. Over here checking the answer. Um,
Well, if we got part A right, part B should not be too bad, should it?
from x equals x naught. Seems less than L over root 2 to make it easier. Down to x equals 0 equals the energy. Okay, so we have to work it from 2 angles. Okay. Verify the work you do. Yeah, I assume those will be pretty short calculations. So we have to use the thing we found for force to get the work, I guess. Oh, that's gonna be an
Yeah.
integral though, because it is changing with distance, right?
Yeah.
So we're going from x naught to 0. Minus 4b squared vx squared over r dx. Um, 4b squared v. Oh, hey, here's my x cubed. I was just zooming ahead to do the work part.
Hmm.
No, 3. There we go. So 4b squared v x naught cubed over 3r. And then we also need to figure out the work from the energy dissipated in the resistor. And so we found the EMF, which is work per charge.
Yeah, I was thinking we had the current as a function of X. Could we use that? We probably have to do another integral. Yeah, EMF should work too, right? I mean, it's kind of some kind of power thing coming from Ohm's law anyway.
Or yeah, I mean, how do we use the current? Oh, do we do current times resistance and integrate it? Oh, now what? Hey, Debian. Edison, you can come back in like an hour, probably like a little bit under an hour. Devon, I can talk about that. Ooh, I don't understand them well myself, but I can talk about that after this. Divergence and curl. The energy dissipated. Okay, I'm thinking if EMF is work per unit charge, could we say that we take the EMF minus 2b xb, multiply it by I dt. Oh, what would we integrate that over though? Well, we know the
Yeah, that's the
velocity.
problem. I was thinking of power as well, but then we'd have to bring time into it.
Um,
Oh, you're
we
saying we could use V? Oh,
oh VDT
there you go.
minus 2bxi dx. And but if we
Now,
were,
do we have to bring
we
I
should plug
in
in
here?
I.
Because
It
I
does depend on
depends on
x.
X. Yeah,
Yeah.
right.
Minus 2b. Oh, it just kind of squares it and puts an r in the denominator. That might not be a bad thing though. 4b squared x squared over r dx. I didn't miss a piece, right? Oh, we get another v. We get a v back, and that's a good thing.
Well, we're good, right? Except we're out by a negative sign. I wasn't sure about that negative sign. So it looks like what you
Yeah.
had in the line above for work.
Should they be opposites? No, they should be the same.
The work you do
Well, we're doing
equals the
positive
energy
work.
dissipated in the resistor. Maybe the signs should be different.
Thanks, Malik. Yeah, I don't know. That's a good question. I don't know. I don't see where we would edit the sign, I guess. I I'm almost willing to just send it and see if the
Yeah.
book says that we're right or wrong.
Yep. Yep.
gonna-
I'm with you.
Okay. I will just write out what our result is going to be and then see what the book says about it.
Should we
Okay.
check units?
Oh yeah, yeah.
I don't really want to.
You don't want? Okay. There's a lot of things to figure out again. Okay, EMF. Basically, they get positive 2bxv for EMF.
Oh, did they?
Why? Oh, because it's already decreasing. Or like dp/dt is already decreasing, and then if you put a negative sign. Yeah.
Oh yes, Don, I changed dx/dt into v, didn't I? I think that was my mistake. Shouldn't that be minus v?
dx/dt into
Because
v.
dx/dt and v are sort of different
Oh,
directions.
they do. Yeah.
Is that right? As v gets bigger, as
V
I
gets
feel like
bigger, x
dx/dt
gets
should have
smaller.
been
Yeah,
negative.
there should be a negative. Okay.
Okay.
Nice. That saves it. And then we introduced another negative sign as soon as we change the I. So there's a negative out front, and then get rid of that negative. Okay. So I do think we must have a little bit like in the initial thing when we're working out d phi dt, because d phi dt is already a negative number, and so the negative, when you put another negative, I think we should have gotten something positive.
Yeah. So you're saying
That, yeah, should
the
have the sign
EMF and the
flipped.
current, they shouldn't have had negatives, right? These two.
Yeah, I think we're consistent, so it's going to end up going away anyway.
Okay.
But yeah, I think we made a small error in the setup there.
Yeah. Well, you say
Uh,
we, you mean me.
well, I didn't see it. Or, I agreed with it. Dude, we're only just now looking at the answer. There's a part B to the question about verifying the work from the force that we calculated versus the work you get from the EMF. But for part A, we got the right expression for E if you ignore the minus sign that we included. It does flow counterclockwise, the current. Okay, they do just use Bill.
Yeah.
I I feel like I do remember them saying that the shape of the wire doesn't matter, but it still makes me uncomfortable.
Or b squared x squared v over r.
Dude, is that what we got?
Yeah. Yeah, we did. We did.
Hey, okay. So
Well,
we were
with some
consistently off
help
with the
from
minus sign.
chaotic.
Wait, what's the three? We need it. We have a. No, sorry, I'm looking at the wrong result. Sorry. Yeah, with some help from chaotic, we did get it right.
Yeah.
Okay. For part A.
I think chat has been on point today.
Yeah.
My goodness.
Okay, so the work from the force is what we did. Since you also can review this stuff. Oh, good. Oh, they do actual power. I squared R?
Well, I was thinking of that. I squared r or v squared over r or
Oh, integrate
or
power with time, and that's energy. Huh. Did we do something? What did we do again? We just did infinitesimal bits of EMF, I guess, which I hope is equivalent.
yeah, no, it is.
Okay. It gets the right answer at least.
All that stuff kind of comes from Ohm's law, right? V equals IR. Except they changed the V into the
Oh,
EMF. So the EMF is the current times the resistance. And you did something really clever though with thinking of it as, what were you saying? It was like force per unit charge or something. Is that what you said?
yeah, that's how EMF is defined, like work per unit
Okay.
charge.
Work per unit charge. Okay. And then you change the charge into current times dt, and then brought in the velocity. That was cool. I like that.
Yeah, I mean, I was kind of making it up as I went along, so I'm glad it worked out.
Even better.
In Dipion, not really. I'm studying it, but I can't really help with physics. But I think I got that because they formally define EMF finally in chapter 7. They talk about it in chapter 4 with Ohm's law, but we only actually just now got the definition with that 1 over q integral thing. So that's what made me think of it. All right, neat problem. Got
Yeah, it was a
another
good one.
half hour.
It was harder than when I first looked at it, I didn't think it would be that hard.
Yeah, I did pick out these problems like late last night, and my brain was a little bit too tired to actually like really read the questions and understand them before I chose them, so I just kind of like winged it. But I'm glad that one seems like a good one. Ooh, okay. I think I'm just doing 6. Another 2-star one. To be honest, definitely have not done that, no. Okay, growing current in the solenoid. Infinite solenoid has radius r and n turns per unit length. The current grows linearly with time according to I of t equals ct. Oh, and c is just an arbitrary constant. I was like, well, wait, capacitance? That doesn't seem right. Use the integral form of Faraday's law to find the electric field at radius r, both inside and outside the solenoid. I should have gotten Faraday's law. That would have been smart. Didn't they write like all the different forms of Faraday's law in one line? Ah, okay. Yeah, but that's different from the differential form, which is... Ugh, okay, I'm going to take a screenshot. Okay, there we go. Oh, I wonder if we want this thing, because if we know the inductance of a solenoid, I think we can say that d phi dt equals L di dt. Hey, Phobos. And we did just do the inductance of this thing actually in number, or whatever the first one we did, I think. The book by S.S. Kratov? Did we all know? It's all doing. Its radius r, n turns per unit length. Just want to verify that thing that I just said, but okay, I mean, do they give us? No, they do it for the rectangular toroidal coil. So the book also has a formula, E equals minus L di dt after applying Faraday's law. So we did find we found the inductance of a solenoid of finite length. If it's infinite length.
Was that the first question we did?
Yeah.
Yeah.
But that question, I think it was number 11, and this question was number 6, so maybe it doesn't rely on that one. Yeah. The thing is, if I think the flux is diverging if we try to do it for an infinite solenoid, because don't we have to draw infinitely many areas? Or infinitely many, like, circles? Maybe this approach isn't it then. Or maybe we're supposed to do something else with it. Um, maybe we are supposed to say b equals mu naught ni and integrate that instead. They just use the integral form of Faraday as well. So I wonder if the inductance constant is a good idea because of that. I imagine what we have to do is like minus d dt integral mu naught ni, like the dot dA, and the dA is what's tripping me up. Like, what surface are we integrating over? Could we draw any surface we want and just do a single circle?
You got me. Don't know.
And if we chose that as our surface, maybe that gives us the EMF drop in just one loop of this infinite solenoid. Oh! Okay, let me go character's name. Might be related to what you were saying last week.
Yeah, this does kind of remind me of what I said last week about a circle inside, fully inside the solenoid, and then one that was
Yeah.
outside.
Okay. Okay. Uh, and they said use the integral form of Faraday's law to verify, or we're trying to find the electric field. So we want, I guess, the middle equalities here. The line integral E dot ds. Okay, so if we start, I guess, with inside. Yeah, this is a really... I forget what problem it was, but I guess it's the same idea as that one we did last week in chapter 6. E times 2 pi r simply, I think, for the line integral. Oh, big R.
All right, I see where you're going here.
It's minus d dt. Mu naught and I because these are all constants. 0 to r. If a is pi r squared, dA is 2 pi r dr. Well, that's just going to give us the area right back out, isn't it?
Yeah, don't you just want pi r squared?
I guess so, yeah. Because that only matters if these weren't constants, I guess. But they are, so pi r squared. Or it's constants with respect to space. The current is changing.
Yeah.
Yeah, I guess we should work that out.
So if I is c times t, then the derivative is just c.
Right. N pi r squared e times 2 pi.
I like this. This feels like the nice old days of Gauss's law.
Yeah. So minus c.
I actually kind of knew what was going on back then.
Yeah, I don't feel like I've been slowly
I
like
think
losing the thread.
you know, I was holding on for grim death until about chapter 4, but once we hit chapter 5, I'm drowning, you know. I don't know what I'm doing anymore.
I'm just pushing through, but yeah,
So
yeah.
that's a capital R, right?
Oh,
That's a
I keep on
capital R.
switching to smaller. You're right.
Yeah, but that's cool.
Um, okay. And so we need to do outside as well.
Wow, look at this. I got a touch screen. Who knew it? I didn't even know I had a
Oh
touch
yeah, the
screen.
laser
Huh.
pointer? Or like what do you mean a touchscreen?
My laptop, I just found out it's a touch screen.
Oh, the one I had in college was like that. I hardly ever used it. Um, oh, it was just like a stylus for that thing. Oh, I guess you already have a tablet though, you said. Um, what's the line integral for the outside ring? Do we just take the entire circumference of the big ring? Shouldn't it be 0? Like, isn't that, well, there's no magnetic field outside an infinite solenoid, I think. Should there be an electric field?
Oh, wait a second now. Yeah, I think I'm confused. I thought you just did outside. You just did inside, did you?
Oh, I thought I was doing inside.
Well, if it was inside, it wouldn't be capital R, would it? It would be small. I mean, it'd be smaller than that.
Should it? I thought that um inside a solenoid, isn't the magnetic field constant? Or is it only on the axis? Or like this thing I'm using only for the axis?
I think it's constant, but I mean, if it's inside, my question is, isn't our little circle that we're taking flux through, isn't that smaller than the radius of the solenoid if we're inside?
I mean, smaller by some infinitesimal amount?
Well, smaller by whatever amount. Don't we want as a function of like the distance from the central axis? Is that what we're trying to find?
Oh.
Use that. Wait a sec. Use the integral form of Faraday's law to find the electric field at radius lowercase r, both inside and outside. Yeah. So we have to consider where it's little r could go to 0, right? Or be any number between
Yeah.
0 and yeah.
Okay, so maybe my brain is telling me to use little r for a reason.
No, the reason I said change it to big R is because I thought we were outside, so it's probably my bad.
No, I
Because I think it's because I was looking at your picture, with the big dotted line outside of it, and I was
yeah,
like, oh, okay, that's yeah.
I'm definitely not organizing my work in a easy to read way. uh, I don't know how this works then for,
Can't
or
we
I
just
forget how
make that
this
outside?
works.
Let's just okay. Wait, I think I got an idea. If we want to make this outside, I think the right hand side, all this would be the same, right? If you're outside, because the area you have to integrate over is just pi capital R squared because it's 0 outside that, right? So I think the
Yeah.
right side is good of what you did, but I think for the left side you want to make that R little r.
Okay. And then we just have
Does
that
that feel
r over
right?
r. I think so.
So now we got to fix the final line here. Yeah, yeah. Does that seem good?
Uh,
Yeah, because that's the thing we were talking about last week. It's like the graph that it comes up like this, and then after you get to
oh,
the R, it falls away as like that, something like that. And I think this one we
yeah.
just got is the second part, the outside part.
Okay. Let me change my label. Okay. And so then for the inside, I guess we would do the same thing, but we use a small r on the right side. Is that the only difference?
Yeah,
That I think that will get us a linear function.
yeah, it feels like it would.
Um,
I'm gonna erase the graph so it's not in your way here.
oh, okay, no worries. All right, so inside is e times 2 pi r equals minus d dt mu naught ni pi small r squared. Yeah. C mu naught n r over 2. I'm just verifying my mental math here. I think it's okay. Because it does match with what we get on the left side if we let big R equal small r.
Yeah.
Okay.
Should it be negative?
We
Our
do get
answer is
negatives
negative.
both ways.
Yeah.
But yeah, are you saying if we should flip the sign again for some reason?
Yeah, I'm not very good with negatives. I always mess them up.
I could see something about like the orientation of no. I think we just get a negative. Well, what does that mean if E is negative?
It means if you put a positive test charge there, it's going to go,
Towards it. Or it'll be
yeah,
attracted.
towards it, doesn't it?
I don't know what direction. I have no intuition for what direction this field is pointing in, I guess. Inside, there should be zero flux with Gauss's law. I don't know. Maybe I shouldn't question it.
I don't know. Let's see if it's verify your answers satisfy the differential form of the law.
Oh, I guess we're gonna have to worry about what
So
direction it points, because how do we get the curl if we don't know the direction? Let me find the expression for curl. Yeah, this is... We need E as a vector.
Okay. Are we in polar coordinates? Cylindrical? Cylindrical, right?
Oh, I guess so. Um, is this going to be... Okay, if we know the magnetic field is always pointing like parallel to the solenoid, say like to the right. E... Oh yeah, for this line, E is going in circles, I think. Because that's... Otherwise the line integral would be 0. So we have a theta hat component, and that matches with what we were doing last week.
Really? I don't remember that. But
Or
I'll take your word for it because
no, I remember we were trying to figure out which components of the cylindrical curl were non-zero,
yeah,
and we
yeah, we were
wanted
doing that.
that's from the
weren't
theta hat piece. Or sorry, uh, I think our E was in the theta hat direction, and so we have like, I guess it would be the dra theta over dr piece that will be non-zero in the curl.
we? Yeah, that's ringing a bell.
Yeah. Um. So I'm gonna slap some theta hats on these E's. So curl E is 1 over R partial R E sub theta partial R Z hat. Okay. Well, that's 0, isn't it? For inside. For outside, it won't be. Or for outside, ugh. We get 0 curl. Because it becomes a constant when you multiply the R into the expression we got there.
Yeah, I see what you mean. Okay.
Does that agree with minus dB dt outside? Well, there is no field outside, or a magnetic field.
I guess it does.
As far as I remember, at least.
Zero equals 0.
All right.
That's good.
As long as 0 equals 0 holds, we're okay.
Hmm.
Um. So there. Okay, I should just write this out, not do it all mentally. We're getting minus c mu naught n r squared over 2. So then we do the derivative. Yeah, we're just gonna get rid of the r. Minus c mu naught n.
Yeah.
Oh, and that's a good thing.
Is that a good thing?
Because when we go to do minus dB dt, I dropped my component vectors. That's mu naught n, negative mu naught ni z hat, and then I is equal to c times t. I forgot to do the partial. Ugh.
Oh, I see times t in this problem, right?
So minus c mu naught n z hat.
Boom.
Okay.
Nice work, Don.
Thank you, thank you. What problem was this?
You're
6.
bringing us home, and you're bringing us home in this reading group. I'm along for the ride here. I'm enjoying it.
Yeah, I'm trying. It'd be cool to make a project out of one of the 4-star problems in this book. I've
Oh
been
my
kind of
God.
thinking about that. I know I'm gonna do it, but um,
They actually have 4-star problems in this book.
you haven't seen them? I guess you
I
haven't been
might
looking
have.
through
I
them.
certainly
Okay.
haven't tried one.
No, me neither.
I don't think I've ever worked out a 3-star yet.
I think early on we were doing 3 stars, like in chapter 1 and 2. They weren't as bad then. I feel like.
Yeah, we did some, but I was never able to do them without
Oh,
any assistance,
yeah. There's that one 4-star problem. I think at least one in each of the chapters when I've been looking through them. Usually like 2 or 3.
This is why I like the more in blue book, I feel like all those problems are 1, maybe 2 stars maximum.
For me, some of them feel like 3 stars.
Do they? Maybe there's a 3. Maybe there's 1 or 2 3s, peppered in there.
Yeah, so some are definitely 1 stars though, where you just like plug things into the formula. For inside the solenoid, they get E theta is mu naught NCR
Yeah.
over 2. Well, why are we negative?
I don't know. I'm feeling pretty negative most of the time here, Maybe that's what happened.
Ah,
Maybe it's just because
oh,
is it
they're
something to do
ignoring
with
the signs. Never mind.
oh, are they? They're just taking the magnitude? Okay.
Yeah.
Oh, ignoring the signs. Well,
Okay.
so yeah.
From Lenz's law, E theta points in the tangential direction opposite to the current flow around the solenoid. Oh, okay. Outside the solenoid, the magnetic flux, blah blah blah. Mu naught NCR squared over 2R. So we got for outside.
Good, good.
Okay. Direction is again opposite to the current flow.
Oh, get out of here. Look, they were negative.
Yeah. I was just getting worried. They
Wow.
started talking about the signs, but we did it right. It's kind of interesting they choose to ignore the signs in the first part and only worry about them after.
Well, I thought these were hard problems today.
I mean, we definitely have tried to do harder ones, so it felt like these ways achievable, and especially the people in chat were helping a lot too,
Yeah.
which makes it smoother.
Thanks, chat.
Yeah, chat carry. Okay. Well, nicely done. So yeah, I will do at least one more meeting on chapter 7. I don't know how I want to divide it like the last few meetings, but I figure with the holidays it's gonna be kind of weird to get things scheduled.
Yeah, I'll try and make it whenever you want to do one.
Okay. Um. But yeah, I guess we'll figure it out when the time comes. But thanks for being here again.
Yeah.
All
All right. I'll see you next time.
All right, see it. Okay. We're gonna switch over to math help now. I was like 2 hours on the dot, basically. Good timing. So I'll switch over to normal math help. Give me 1 minute to switch title and category. Yeah, Traveling Jack. Yeah, we'll see who's here right now because there are 2 people in the YouTube chat. So I dual stream to Twitch and YouTube. There are 2 people in YouTube chat who are asking about math help as well, but you're here right now, so we'll probably start with you. Ooh, I need to export this. PNG. Am I all switched over? I think I am. Okay, so Traveling Jack, you're saying 0.99 equals 1 proves either simplistic. 1/3 times 3 equals 1. 1/3 equals 0.33. Ha! That is funny. You take issue with the fact that 1/3 is equal to 0.33. Why is that? I'm going to type to the people on YouTube who were asking about math help earlier. Trying to resolve a base 3 number in decimal form or by a base 10 system. You are losing something in the translation. Yeah, I mean, I could see that where, I mean, that's definitely worthy of raising a question. I've heard them saying whether that proof is right or wrong, but there is a proof that I've seen that I can't really argue with. Yeah, exactly. It's basically what FizzBuzz is saying. So like 0.9999, you can think of it as equal to 0.9 plus 0.09 plus 0.009 plus, you know, dot dot dot. And that's expressible as a series. And it's expressible as a series that we know the sum of. Uh, that's a 9/10 times 1/10 to the n. That's just like getting around our by defining them away. Oh, you're really defining it like that. Yeah, I mean, I guess you could do that. One third equals 3/10 to the n, where 10 to the n equals 9. Uh, well, sure, that's not an integer. There's a log. Or there's like a real number where that's true. So like the representation in base 10 is flawed, but I don't think it's... I think this fact is true irrespective of base. Like the base is just showing the same thing in a different way. Like I don't think changing the base of the number actually does all that much for you. I mean, I don't know. I just chalk it up to weird things happen when you let things go to infinity. Well, okay, if you don't believe in infinite, like, yes, infinity isn't a number, but the concept does exist. A lot of math relies on it. Yeah, Mina, we're talking to Traveling Jack about the whole idea of why does 0.999 equal 1? I think it's more that your base 10 representation, maybe it's that your base 10 representation of 1/3 isn't right. Or there's another way of saying it, which is I mean, it's not just one thing, it's 3/10 plus 3/100, 3/1000. Abrego announces haunting me. They are exactly equal if you go out to infinity. I feel like you're kind of getting at the idea of convergence. Like, if you take just this, like, say that's the number of terms and that's the sum up to that term. If you take just the 3/10, say you're right there. If you take the first two terms, you go a little bit further up. If you take the first three terms, you go a little further up, and you're going to eventually get a curve that like levels off like this. And it's going to be upper bounded by 1/3. But like, you can get as arbitrarily close to 1/3 as you like with this progression. That's what it means to be convergent. And you can make that remainder as close to 0 as you like. And since you can make the remainder as close to 0 as you like, it means that you're, if you let things go to infinity, they're exactly equal. That's the weird kind of leap that you do in analysis, but as far as I know, that's just how it works. Yeah, Lubert has it. For a finite number as close to 0 without actually hitting it. Infinity minus 1? I don't know what you mean with that. Like, infinity minus 1 is still infinity. I assume it's the point that you're making, but I don't know what that point is. Well, yeah, Traveling Jack. Like the argument is that for for any precision you want to make me get, I can always get that much precision in the decimals. I can describe an algorithmic process that will reach any desired precision you want. I can make the right side of this as close to 0.33 as you want. And I can do that in an arbitrary way that's not like that's repeatable infinitely many times. Or, you know, like I a better word is maybe arbitrary than an infinity. For anything, because I've heard Zach make this point, eats the 2i pi, that he probably explained this better than I could, to be honest, but I guess in a way you're right, where it's not necessarily like, you know, infinity isn't a number, it doesn't exist, but you can get arbitrarily big. If I say that, you know, if you say to, or if I say that this is 0.33, or at least pretty dang close, and you say that's not good enough, I'll say, okay, well, I'll just do the same thing, but add another term. And if you say that's not good enough, then I'll add on another term after that. And like, no matter how precise you want to be, I can always just add on one more term. Like that's the idea. I don't think that's the right representation for 1/3 in base 10. Like, that's just one of these terms here. Am I doing it right in base 10? Wait. Oh, am I wrong with this? It's something about this isn't quite right. Right? No, it is right. Never mind. Never mind. Yeah. I think your representation of 1/3 in base 10 isn't right. Let me read what was said earlier. Sum of 3/10 to the n from n equals 1 to infinity is defined as the number s. Critical, yeah. Critical, sure. N equals 1 to infinity is defined as a number s such that for every epsilon greater than 0 there exists an n such that for all m greater than n, s minus the sum. And yeah, it's just like the epsilon n definition for a limit, right? Like that's what I mean with like an algorithm to, like the algorithm I'm saying is to find that n. It is awkward to represent a number like this in base 10. That doesn't mean it's wrong. I like, I agree with your feeling that, like, I don't like this. But as far as I know, it is true, and that's just because this representation in base 10 is awkward. I guess. Yeah. As n approaches positive infinity, 0.33 might. Well, I think you're working backwards there, Joseph. Like the 1 over 1 plus n feels kind of random. By call, I'm going to use the whole thing. I'm still going to try to continue the discussion. I'm going to take a look at Critical's question, though. There isn't anything missing, but there is a dot dot dot, and that's what makes the difference. Why the Q has 10 to the minus 9? Also explain the... Oh, I mean, I'm pretty sure I'll just call it an ellipsis. Or ellipse. So you're trying to explain those two parts in the lower right. Well, the 10 to the minus 9 is because it's 3 nanocoulombs. 3 nanocoulombs is equal to 3 times, oh my god, 3 times 10 to the minus 9 coulombs. That's just metric unit conversions. Nano basically means 10 to the minus 9. And then that piece, like, just where it comes from the integral up here. Whoa. Is that your question for where it comes from? Or I don't know what you're asking about the other part. Why is there an integral sign? Because it's just this is the real definition of work, which is that work is the integral of force over distance. Like, you may have been taught before calculus that work is force times distance, but that isn't true if your force also change is if your force is changing. Like, they always assume the force is constant when they give you this formula. But the force depends on distance, and so this is the actual formula for work, because force often does depend on distance. That's just how it's defined, and they give you that simpler version of the formula before you learn calculus, because you haven't learned calculus yet. I mean, it is possible, but like the integral version is more general. Like, it also includes that constant force case inside it. It's like the bottom one is one of the simplifications they make to help you out when you haven't learned the math yet. But once you learn the math, you get to use the more general version of things. So I don't know if it's maybe unrealistic is the wrong word, but it's just like the integral version is always applicable, whereas the bottom version is only applicable to a constant force. Or there's a force that doesn't change with distance, but this force definitely does change with distance between two particles. Yeah, that piece comes from evaluating the bounds of the integral. So you first take that r equal to r2, then subtract and take it equal to r1. Yeah. Is that everything you had to ask there, critical? Is there something more here? I don't see critical typing, so I'm gonna assume that we're good. Okay. Yep. No worries. Um, All right. I don't know what to say about your thing, Trap and Jack. Hmm. Maybe. I wonder about something. So Captain Jack was saying that like a counterpoint. I'm sorry, Captain Jack. Trap on Jack was saying is that there is no n such that 1/3 equals 3/10 to the n, and that's true. But or basically, there's no integer such that 10 to the n equals 9. But there is a real number, and I'm just kind of curious. Um, like, what I want, I'm kind of curious if a power series would actually help with this. If this is going to give us another infinite thing, or because I don't agree that this is true for an integer n. I don't think this is the proper base 10 representation of 1/3. But I'm curious if we could force it to be like that. Um, if you use an approximation for log. Writing log base e feels so wrong. Well, so, I mean, it's not fair to say that every base 10 decimal should be able to be represented by a single fraction. 0.45 is equal to 4/10 plus 5/10, or 5/100. That's kind of like my issue with it. Unless I'm misinterpreting you there, but... This isn't actually as helpful as I thought it'd be. And then I just wrote. If 3 over 10 to the n equals 0.3 repeating, but it's not actually equal to 1/3, then we might be able to find the remainder if we can figure out that last part. I really don't understand that. I don't understand what you're saying with that being the what's missing part. There's an unresolved main. I think we can just do some long division, can't we? Like, you're how are we ever going to get a remainder? Like, there's never going to be a remainder. Unless you're talking about the 3's that we're leaving off, because we're only doing, if we only do a finite. Well, the entire point is it's only true when you go out to infinity. The thing we care about is that it's infinitely repeatable. Not that you have to execute it by hand, but that you could execute it. It always has a remainder unless you do go to infinity where it has no remainder. Yep. I'm certain of that. That's just how convergence works. Like, if I were just to write 0.33333, like if I were to do this long division out to infinity, it would take me infinite time. But if I spent like, the entire rest of time doing this, you would never be able to tell me that I'm wrong because I'm still going. That'll be a pretty hellish existence. Doing this. It's like if a mathematician gets sent to hell, you have to just prove that 1/3 equals 0.3 repeating by doing this long division. It's kind of a cop-out. I mean, math is full of cop-outs, and if that's your attitude, I guess. I think mathematicians love cop-outs. That's just called a clever proof. A cop-out. Like, why do it the easy way? Or why do it the hard way if you can do it the easy way? I mean, I love a good trick to like prove something. This particular argument I feel like is pretty unimportant. Like no matter what the result is, I don't like particularly care, I guess. Like, nah, who cares? Yep, no worries, traveling Jack. Like, there's a lot of things in math that are just weird when you consider infinity. If you get into like set theory and stuff like that, there's many more like lively debates on the meaning and like the utility of infinity, I guess. This one is just like a fun fact that got like spewed out on the internet for a while and became like a small meme, I guess. But I don't know. I studied applied math, and that's math that I care a lot more about personally. But either way, welcome into the stream, and thanks for asking that question. Yes, sounds good. Yeah, the people in the YouTube chat haven't turned back up yet, unfortunately. So I do have a hard stop. Oh, I'm gonna have to turn the stream off maybe half an hour or so. I don't want to do. I can maybe go a bit longer, but and in the meantime, we'll do a little bit of physics studying, just mechanics rather than E&M. This is the last problem in chapter 3. Actually, I did skip a problem that I could go back to, but I also don't want to. Hey, Scorpa. Sounds good. Traveling Jack. Enjoyed the movie. Hmm. Okay. So that's our hoop. We have a bead that magically stays attached to the hoop. I really like if this hoop is frictionless, does the bead steer like? I guess it depends on the size of the push, but like, would the bead seriously just go around in circles infinitely many times if there's no friction? That seems weird to me. Like, if the hoop is big enough, it should just like fall straight down and not follow it. But I guess if the hoop is small enough, then maybe it'll follow along the curve and like get caught in the lower part of the hoop and then start accelerating or something. I don't know. Okay, so they're asking where the bead's total acceleration is horizontal. At every point, it's going to have not use that color. An inward radial acceleration. And it'll also have a tangential acceleration that depends on gravity and where it is in the loop. So it's going to be like g, sine theta or cosine theta or something. God damn it, I have to pee. Okay, fine. I'm gonna go pee. I'm gonna be right back, guys. Okay. Sorry about that. If I define theta to be, say, like the angle measured counterclockwise from the top, that's a really light green. The acceleration, the tangential acceleration at any time t, I have to decide between sine or cosine. I'm thinking cosine. Am I thinking that? At 0, it should be exactly g, right? No. It's sine. Because the tangential acceleration is exactly g right on either side. The tangential acceleration at the top and bottom is 0. And how does the sign of this, the SIG end of this SINE work out? It does flip from... Do I need an absolute value here? Is that what you're telling me? Because it should always be negative. No, ooh, wait, should it? Should it? The tangential acceleration. So if we're traveling counterclockwise around the circle, tangential acceleration... It does flip directions. So maybe we don't need an absolute value. Because it's speeding up in the first half and slowing down in the second half. Okay. No absolute value then. So we certainly have... Well, what do we have? The radial acceleration, that's v squared over r. And they give us this formula for the height. Or for v after falling a height h. It is v squared over r, right? The units are right. Yeah, v squared over r. It does it? Ooh, so what about the sign here? I think we maybe need to make it piecewise. No, I think maybe the vector. With magnitude is always 2gh over r. Is it? Is the velocity at this point the same as the velocity, or wait. I'm trying to figure out if this applies to both halves of the circles, of the circle. Radial acceleration. Or rather, I guess... I think we're okay on the signs. I think. I feel like we are. I have a hard time saying why. I just feel like it'd be too weird to worry about signs. And if it's horizontal, do we want arctan of something over something to be something? What does it mean to be horizontal? It means You know, it might be the A vector is 2gh over r hat plus g sine theta hat, right? The angle between those two unit vectors is always 90. I'm doing good, Anon. What is my screen time in a day? A lot. I used to spend all day at my computer. And my eyes are steadily getting worse, so I don't know. 12 hours, something? I don't know. We have to work with these stupid r hat theta hat vectors again, and I'm so bad at using them. We want to find when the entire thing is horizontal. So it could be horizontal if the theta hat component is 0, right? And it could also be horizontal wait. It could be horizontal if A T, no. It could be horizontal if if AR is 0, and AT is not 0, the tangential well, fuck. At the top and bottom, I think we have 0. No. At the top and bottom, we have 0 tangential acceleration. Okay. So that's not... It's not the top and bottom. It could be on the left and right sides because the tangential acceleration has to be 0, and that's not true. In fact, tangential is at its peak. Okay. Well, that's useless. So it's not at the like north, south, east, west directions. It's somewhere in between. I'm trying to think about what it means, how we can represent a horizontal vector in polar vectors. Because the base our hat and theta depend on where you are on the circles. Like how, like I don't get how you work with these things. I really they make some of the representations really convenient, but I don't know how to interpret them. Um, I don't know how to like really use them. I guess I kind of know how to interpret them. At any points x and y, like, hmm, can we like? If this feels like, is it possible? Can we translate polar vectors to Cartesian vectors? Because letting the y component of a Cartesian vector equal 0 seems really easy. What does the book say about? They do have an appendix that briefly covers polar vectors. Yeah, I think the appendix isn't that helpful here. Okay, you are not very helpful, appendix. um, this is really annoying. So I feel like I should know this, or like there's a really similar problem to this earlier on that I got wrong, and I really want to get this one right. And I think I'm off to the right start because I think they did the same g sine theta thing that I did. He does that press. Hmm. Can we always find like a Cartesian representation? Like I feel like we just have to be able to translate this to Cartesian. I don't see how we can possibly figure out horizontally the horizontal direction easily with these polar things. Because like what I would want to do is say the magnitudes have to add up to give us a particular like balance between r hat and theta hat, but r hat and theta hat themselves vary. So yeah, I think what everything I've written so far is true. I just it's the next step that I'm stuck on. Like um I assume we need to find Cartesian representations for AR and AT. I just don't know how else we could do this. We know that x squared plus y squared is r squared. Tangent to a circle. And normal to a circle. Just quit studying and play video games. True. That sounds great. I love it. Video games with this prep for the JE is killing me. I bet, to be honest. The JE looks insane. I wonder why I spend so much time trying to figure stuff out when it's so often frustrating. It is productive. I feel like this is like a good use of time to try and learn stuff. Motivate you? I think I'm a bad person to ask for motivation on that. I had no motivation to take my uni entrance exam. I didn't study for it. But you should, okay, I should try to motivate you though. You should study because it is a good idea and will help you out in the future. Here's the time looking back, but it's frustrating looking forward. Yeah, that's. So you're saying that you need to learn relativity, and then if you ever get frustrated, just try to move at a faster speed or something. I don't know. I try to make some kind of joke with like speeding up or slowing down time, but it's not really coming to me. Frustration is relative. There you go. Like, I was thinking that getting the slope of the tangent is maybe helpful, but also how is it helpful? When I'm playing video games, I say the opposite. There's no winning. Oh my god. That's real, Fizzbuzz. That's real. Such is life. What? I kind of wonder, like, I almost want to put this slope of the tangent somehow equal to the tangential acceleration, but I can't really justify it. It's not like I need to do something else with this before I can say it's equal to tangential acceleration. I think. Why don't you use vectors and take the dot product? I only really have one vector to work with that I can see. Oh, but if I can define a vector that's horizontal. Well, how do I do that in r hat and theta hat? That's my issue. That is a neat idea. I would need to dot it with a horizontal polar vector and find where the angle between them is 0. I can't, I don't know the Cartesian representation. That's the issue. That's what I'm trying to figure out. Am I being stupid? We can't say that it's g sine theta, g cosine theta, right? No, we can't. No. There's no way. No way, right? It might actually be that. Well, Tipion, yeah, I mean the centripetal tangential is in polar vectors though. Like that's kind of my issue. If this thing that I wrote in Cartesian is true, I think that will be great. Is it? No, it's not. It can't be true. I don't think it is. I don't like this either. Well, I don't know how to do that, to be honest. That's the issue. That's what I've been trying to figure out this entire time. This is gonna give me polar coordinates, I bet. Oh, really? That seems helpful. Why don't they tell us that in the book? Are you kidding me, Morin? Am I supposed to know this? I'm gonna check the answer and like Morin's gonna say how I should have figured it out. All right, if I just I have no idea if this state is the same. I'm gonna pretend it is because it's just more convenient for me if I can. All four on the unit circle. Sure. I still don't know how to work out like what components go where, but so what are our I components? Which I guess aren't important. As well, we have to make sure they're not zero at the same spots. All right, well, if this thing is true, then we can just set j equal to 0 and make sure that I isn't 0 at the same time. They're just I and j rotated by theta. Okay. So the sine theta, I think we get garbage. But, mental math, don't fail me. Is that R or K? Who knows? What's the difference? G drops out entirely. I guess it has to because of the units. I feel like there's some going to be weird identity where arc cosine of a negative thing is equal to arc sine of that thing, but I don't know. I think we're going to throw these out because, well, be careful with H. What's wrong with H? H and theta. They're probably not independent. No, you're right. We could probably write our H in terms of R in theta. Ugh. It depends what quadrant we're in, I guess, right? That's the annoying bit. And as soon as we take an arc cosine, like I was just trying to figure out what quadrant we're going to be in. Like this arc cosine might not, like there's an interpretation we have to do here. I mean, if it's arc cosine of a negative thing, does that mean we're getting a solution like somewhere down here? Asymmetrically, we should have another solution over here. Does that make intuitive sense? Could we have... yeah, I think that makes intuitive sense because if we're up here, there's no way we can add the tangential and radial vectors together to get something horizontal. They're both pointing down. Our only chance to be horizontal is in the lower half when they point like that, and then you have a chance of canceling out when the magnitudes are just right. So if we are, let's go to a third color. If we are down here, H. Whoa. My eyes are playing tricks on me. This little blue bit here looks green to me because it's between the green bits. That's so weird. That's like an optical illusion. Um, so we want pi minus theta is the angle inside here. Oh, I didn't draw my blue theta line correctly anyway. That angle right there is theta. Yeah. So we can say that in the second and third quadrants, because kind of my bottom two quadrants, that cosine pi minus theta equals h over r. What is cosine pi minus theta? That's a trig identity, right? If you shift it by x and reflect it, isn't it just cosine theta? I feel like it's just cosine theta. What is j hat? Cosine x. No, never mind. It's cosine of negative x. We can work with that though. No, it's negative cosine x. Okay. X theta. So then that means h is equal to minus r cosine theta. In the quadrant we're working in. This seems... like a thing. Arc cosine of 2 cosine theta. I don't know how to interpret that. I don't think I set this up right. That's not what h is. I didn't do this right. I didn't define h right. H isn't that. H is the entire distance from the top down to the bottom of that light blue triangle. J is the unit vector in y-axis? I don't know what happens when you dot vectors with different bases. I feel like that just doesn't work. Hey, Phobos. Yeah, it is. I made good progress on this problem, but I feel like I'm near to the end, but I need to figure out a relationship between the vertical displacement in this circle and the angle theta. And I'm gonna have to go soon. Full of doubt in my physics chops. Yep. Morin lives rent free in my head. Living a life of debauchery. um, at the top and bottom of the hoop. So I'm pretty sure the answer is it's going to be somewhere here and symmetrically somewhere here. I'm working on trying to find that point, and then it'll be easy to find the other point. It's not at the top and bottom, because at the top and bottom we have our radial acceleration inward, and the tangential acceleration is 0, both at the top and bottom. So the acceleration is just the radially inward. It's only vertical, actually. And so I think intuitively it should be somewhere around here, because the tangential acceleration points out like that, and the radial acceleration points like that. And so there should be a sweet spot where the magnitudes line up just to get a horizontal vector when you add them. And I think I have something that represents that, but I want to get rid of... Or I think I found that to represent it, but I want to get rid of H, because I think H is secretly a function of theta, or Fenbox pointed out that it probably is. But the geometry is a little bit weird. And that thing I wrote right below it is just wrong. H is vertical displacement after it has fallen through a height h. So I guess what I want to do is like set up this triangle, and that entire blue side there is H, but I don't know really anything else about this triangle. Oh yeah, there you go, Phobos. I feel like in that cartoon in Adventure Time, they said something similar. I didn't really watch it though. I just remember like hearing quotes. Ah, crap, I actually have to go. I'm out of time. Or like not like completely out of time, but like I got plans with my friends, and I think my friends actually aren't going to flake this time for once in their lives. Um, yeah, I could maybe. Oh, so wait, the triangle I did before is maybe okay. I just needed to remember that was an H. Okay. Krastic, I see you. Let me. Uh, that's theta. This is just some other thing. We can call it D. And D plus R is H. Crap. Okay, but I'm not turning the stream off quite yet. Let me, Krasik, I'm not gonna have enough time to explain that. I'm sorry. I can link you to this to pause all my notes that I really like though. I'm sorry, it's just like a bad time where I have to turn the stream off soon, and I'm also really invested in this problem that I want to try and get through. But I looked through the examples there and the pictures that they have. I'm sorry about that. That's a really crappy response to give to someone, but it's just a weird time. Okay, so this is where I can say, where is my cursor? There it is. Cosine pi minus theta equals d over r. Cosine pi minus theta equals, and d is h minus r? Yeah. Over r. And that's what I need, right? It is. It's so like small. And so cosine of pi minus something is equal to negative cosine of that thing. So wait, what does that mean h equals? H equals r plus r, no, minus. R minus r cosine theta. That's what I'm claiming. R cosine, the r's cancel. 2 cosine theta minus 2. I don't want to simplify that. Oh, maybe we don't want to take arc cosine of each side yet. Yeah. 2gh over r. Like, apply it here, like Fenbox says. The g's divide out. The r in the first part cancels. 2 minus 2 cosine theta plus cosine theta. Is that what we get? G's divide out. The r divides out from there. Okay. 2 minus cosine theta equals 0. Oh, come on! Alright, you know, fuck this. But cosine theta equals 2. Okay. I'm leaving. God damn it. I felt so good about that. Then I get cosine theta equals 2. Okay, I'm cutting the YouTube show up here. If you're on YouTube, thank you and bye.